you were considering future career pathways, as you do, and you stumbled across industrial design, and it looks pretty interesting. So to start pursuing this, you got a 3D printer. I have one, and I would strongly recommend getting one. I have the Ender 3 V2. It's very nice. Cheap too. Well, relatively. And anyway, you get one and you start prototyping a phone docking station. Now, the printer works by moving a print head in the X and Y directions while pushing out melted plastic. Right, and it just builds up layers upon layers until your prototype is done. And we're told that the print head accelerates from rest to a speed of 0.1 meters per second in 0.01 seconds. And it has a mass of 400 grams. Calculate the gain in kinetic energy. So we're given a mass and we are given a speed. We're also given a time. Now, kinetic energy, we know it relates to the mass and speed of an object by half mv squared. So we can substitute in mass and in speed to solve for kinetic energy. So in this case, half times, is it 400? Right, convert to SI units. So 0.4 kgs. 0.4 times speed, that's already in SI units. So that's all good. 0.1 all squared. So now we can compute that. So half times 0.4 times 0.1 squared gives 2 times 10 to the negative 3. And what would the units for that be? Kinetic energy, so energy is measured in joules. Well, that's the SI unit, and since we used SI units, our output will also be in SI units. That is the beauty of SI units. Alright, so we've got our kinetic energy. Now, part 2, calculate the power output of the motor required for this acceleration. So to move the print head, it actually usually runs along belts, and at one end of the belt we have a electric motor. Alright, so it can spin, turns the belt, which then is attached to the print head, so the print head moves as needed. So to gain this kinetic energy, of course, the motor itself needs to supply it, and it has a power rating, which is how much energy it can supply every second. So looking at our formula sheet for inspiration, we recall that power is energy over time, or work over time, where work is just how much energy you transferred, right? So there, in this case, the motor transferred, the printer head gained kinetic energy, so that would be its work done. And we are given time, right? Because it did this maneuver in 0.01 seconds. So the power output would be the kinetic energy that the printer had gained divided by how long it took it to gain that energy. And what's that? So that's 1/10, 100th. So it's the same as timesing the numerator by 100. So that should be 0.2. Let's see. So divided by 0.01. Genius. So what are the units for that? Yep. What are the units for that? Alright, show's over. So we've worked out the power output of the motor. Kind of. So part 3 is to explain why the power output of the motor actually needs to be much greater than this. So 0.2 watts was enough for this particular maneuver, right? But in reality, motors are often rated a lot more powerful than they need to be, right, for safety reasons. And in the real life, there are, of course, power losses. So like in the belt, there'll be some heat loss due to friction, sound, etc., which means the motor needs to be more powerful. So let's bullet point that. So motor needs to be more powerful, or let's say it needs to have a higher power output, just so we're clear. It needs to have a higher power output than in part 2, because it may need to perform faster operations. So we were just given one example of the printer head moving, but it might need to move it faster in less time. So it would need a higher power output to do that. Because it also makes it safer, and because there are energy losses to heat and friction. Right, so all of these 3 reasons are why the motor would actually, in reality, have a higher power output. And there's also things like manufacturing, right? Certain manufacturers build motors a certain way, and then other people use them for 3D printers, which don't actually need that much power. But it is what it is. Alright, and part B, the print is now done, and you have this prototype. Wonderful. But you take physics, and you're interested in engineering, so you want to test its strength before you move on. And you do this by hanging masses from it and measuring how much it bends or deflects. And for one trial, you hang 200 grams from it, and it bends by 0.008 meters. Calculate its elastic potential energy. So let's draw a diagram for that. Now, it does depend what kind of phone docking station you have in your mind, but I'm just thinking like maybe a flattish one where your charging port goes there and it's got like an indent in it so your phone can sit upright. Right, so here's your phone, something like that. And of course you'd need to stick it down to the desk so it doesn't flop over. But so here's our design, and you are hanging masses from it. Something like that. Let's draw our straps a bit better. There we go. You got to use your imagination with my drawing. Oh my goodness, what is this? There we go. 200 grams. That's as clear as it's going to be. And in our phone docking station, it bends slightly. So that red line is how it's deformed. I've exaggerated it, right? In reality, it won't bend half of its height, but just so we can see. And that bend is 0.008 meters. There we go. And we are looking for the elastic potential energy that the docking station has when it's bent that much. So it's essentially acting like a spring. So looking at our formula sheet, to calculate elastic potential energy of a spring, we need the spring constant, which is a property of the spring or the material, which we don't have, and we need how much it's deflected from equilibrium, which we do know, and that's 0.008 meters. So how do we find K? By Hooke's law, we know that the force required to stretch a spring by some distance is related to its spring constant. So in this case, the force on the spring is actually provided by the mass because it has a weight force down. So on the docking station, it's pulling it down. So instead of force, we will label that as M times G, right? The weight force acting on the docking station. And we know what M and G are, right? 200 grams times 9.8. Now, converting to SI units first, 0.2 times 9.8 equals negative K and X, that's 0.008. So we formed an equation where the only thing unknown is K, so we can solve. Divide both sides by 0.008 equals K. And just a note on this negative sign, what that tells us in Hooke's law is that when you pull a string, let's say to the right, the force, the restoring force that the spring is providing is to the left, right? Negative just indicates if we move it to the right, the force will be to the left. And if you compress a string, so you push it to the left, it's going to want to push back to the right. But so if we're solving for the spring constant, we can omit the negative sign. And so let's calculate this. 0.2 times 9.8 divided by 0.008 gives 245, and the spring constant is force divided by a distance, so newtons per meter for our units. Now the question didn't ask us to find this, however we did need it to then now solve for the potential energy stored inside of our docking station as it's stretched. So half times K times the distance it's been stretched squared. So timesing by a half, timesing by the distance it has been stretched squared. So 245 times half times 0.008 squared. 7.84 times 10 to the negative 3. And now, what are the units for that? Energy is in joules. Now, what should we round it to? Well, this distance is to one significant figure, and so is the mass. So to one significant figure, 8 times 10 to the negative 3 joules. Right? Which isn't much, but that's to be expected because our docking station stretched a very small amount, and the potential energy is actually proportional to the distance squared. Yeah, so that is to be expected. Alrighty, and then we're done. So we've tested it, it's strong enough, time to produce it, make millions of dollars, and see you next time.